Um, so what we stopped talking about, hopefully fresh in your minds, is reliable transport in dealing with the transport layer, right? And in terms of providing reliable transport, quick recap, what kind of stuff did we talk about, or what's used by TCP? Do you remember? This should be all in your heads now. How do you do reliable transport? We use, what do we need? All burnt out. Should be refreshed. How do you do reliable transport? What are the elements we need to implement reliable transport? What have you been doing in assignment 2? So acknowledgements, right? So between the sender and receiver. What else did you guys do? Checksum to detect something is corrupt, and you were told to implement a checksum on your own, right? And then make sure it works. Hopefully you did that. And it was fairly straightforward. You could just use simple integer addition. That would have worked well. What else? Anything else? Reliable transport. Sequence numbers. Okay, why did you guys use sequence numbers? In order delivery. Yes. What did you guys use sequence numbers?
So you know where you're up to in a window.
You know where you're up to in a window. Anything else?
Detect duplicates.
Detect duplicates, right? Because when we had retransmissions, we wanted to make sure that we understood whether that packet is something we already had or whether it was a new packet, right? So detect duplicates, we use sequence numbers. And then it got tricky for you. When you did alternating bit, it was easy. How many sequence numbers did you use for alternating bit? Huh? Twos. What were they? 0 and 1. So it got a little trickier when you had to, alternating bit is not so good. Why is alternating bit not so good in terms of a reliable transport delivery mechanism? Slow, that's right. Why is it slow? It's like stop and wait, right? Stop and go. So you send something, you wait, when you get it back, you send it. So the thing to fix this was to do what? How do we get more throughput from a big link? Pipelining, thank you. So pipelining was the way to go. But when we started pipelining, we were going to run into problems, right? That's why we needed sequence numbers to distinguish packets that were not being acknowledged, but still send down the link. So the way you guys did implement pipelining was using a simple protocol called go back in. So, and I asked you guys, gave you some hints and an example, and I told you to think about what might be the window size you need if you were implementing go back in. So what was the window size you guys used for go back in? 6, okay. And that is, how do you get 6? It was in the spec, really? Why use 6? What's the relationship between window size and the number of sequence numbers for go back in? Window size plus 1, right. So why do we need window size plus 1? Where's the plus 1 coming from? Yes.
Even X 0, because of a failure, you'll see that your entire window was just discarded and skipped.
So essentially, if that ACK gets lost, but you have the sender has refilled that 0, it's reused that sequence number, the receiver can't tell the difference between the old and the new. So I put up a simple example in the announcements. And if you work through that example, you'll arrive at the same conclusion that you need the sequence numbers to be the window size plus 1, 1 being the window size of the receiver, right? So the total number of packets that you need to distinguish uniquely is what the sender's window size is, how many packets it can send simultaneously. No, well, at one time, plus how many packets the receiver is buffering, right? So it's not hard to see why that is the case. So imagine you had a window size of 3. This is the example pretty much I posted. Okay, so you had sequence numbers 0, 1, and 2. So W is equal to 3, right? And then imagine that you had sent these packets. So you send 0, 1, and 2. Send the receiver, and consider that all the X are 1, 2, and 3. All the X are lost, right? But from a receiver's point of view, the receiver has got a 0, and it sends to the application layer. Receiver has got 1, sends to the application layer. Receiver has got 2, sends to the application layer. So now it's expecting 0 again, right? Yeah. Okay. So if all these X are lost, what happens to the sender? The sender still is waiting for acknowledgements for sequence 0, 1, and 2, and then a timeout event will occur, right? For the first sent packet, which is 0 in this case. Okay, so there will be a timeout. And then what will the sender do? You should, resend the entire window, right? So we'll resend these packets 1, 2, 3 again. So that's a 0, 1, and 2. Now the receiver is waiting for 0, right? So it will think this retransmitted packet is a new packet, right? Yes? Can you see the problem? Right? So if you want to distinguish this case, you need to have, as you were saying, window +1. Hey, how you doing? You guys all right? We can have a chat afterwards. So this will be window +1. So hopefully you should have all arrived at this conclusion just following the simple example and realize that you have to use window +1. Worst case, you Googled it and found a solution, right? So in case of go back n, GBN, the sequence number space, right? Numbers really need to be greater than or equal to window size +1. But when you look at, so we looked at selective repeat briefly. If you remember, in selective repeat, there's a sender window and a receiver window, right? So you can see that this is the sender window, this is the receiver window, and this is kind of trying to solve the problem with go back n, which is go back n just sends the entire window, right, when an acknowledgement doesn't arrive, which is kind of wasteful because sometimes some packets get through, but go back n expects everything to be received in order, right? So the way selective repeat solves this by individually acknowledging packets. So if you don't remember how that works, so it sends packets, and it individually it individually acknowledges packets, right? So you can see that one timed out and got retransmitted, but we didn't retransmit the entire window like in go back in, right? So this saves bandwidth, right? You're not wastefully retransmitting successfully received packets, right? So that's the solution that selective repeat provides, okay? Now, if you were looking at selective repeat, what should be the window size for selective repeat? Or in other words, ask yourself, how many packets do we need to distinguish in selective repeat so that you didn't get confused with old packets and new packets?
Do you mean sequence numbers, please?
Yeah, how many sequence numbers do you need? What's the relationship between window size and sequence numbers for selective repeat, in other words? So you still have a window size W, right? In this case, 1, here it should be 5. And then the receiver has a window size of 5, right? So this is W and this is W. So how many sequence numbers will we need to distinguish packets individually in this case? Sorry? Oh, sorry, thanks. I was trying to put a face to the voice. Yeah, twice the window size, but why? What could go wrong here if you use any less? Or did you just guess that? Or just in your mind? Yeah, well, it's good. Yes.
The window size of the sender is the packets that haven't yet been allocated.
Yeah.
Whereas the receiver's expecting new packets. So you need both, because in case the receiver receives all of them, and then all of the transmissions are lost,
Yeah.
then the sender could send all of them again. And if they're interpreted inside that window, then it will be interpreted as a new packet.
Yeah, so what he said, in other words, basically you have two consecutive windows, right? You can send this one, and then you have another one, right? So remember the sequence numbers repeat for two consecutive windows. And the receiver must be able to distinguish those, because they might overlap, right? Because of X being lost. So you need to be able to distinguish consecutive windows, right? You can play, if you're not convinced, you can do the same kind of example as what I did and convince yourself that that is the case. So in terms of selective repeat, right, sequence numbers must be greater than 2 times the window size. Why? Because consecutive windows so what that means is that you have a window here, but then these are the, so this is, you can say currently unact, and this is maybe to be sent, right? So remember, receiver has size W. So the receiver needs to be able to tell the difference between this window and this window, right? Okay? So the answer to the question of window size versus range of sequence numbers really depends on the type of protocol, the type of reliability transfer protocol that you're using, type of pipelining that you're using, the type of pipeline that you're using, pipelining method that you're using, and needs a little bit of thinking, right? So there is a lower bound on the number of sequence numbers, and hopefully that part is very clear. Do you have any questions on this so far? So you guys are experts now. So what are some of the consequences of pipelining, right? So you already know the consequences of pipelining. One is, of course, you need to increase sequence numbers, right? This you've seen with GBN and selective repeat, right? Because you may have a large number of in-transit and unacknowledged packets. What else did you need to do as a result of pipelining when you went from alternating bit to GBN on your sender side? When you change your code from, yeah. You don't change how it works with X, but what did you need to do in terms of state?
Oh, the timer always has to be based on the last or the oldest packet.
Yeah, so you had to, so you need to manage, you need to always time the oldest packet, so that's, And then when you get ACK, then you had a whole bunch of other packets of time, right? Because typically you want to implement it with a single timer, not multiple timers. It's more expensive. Something else you had to do when you went from alternating bit to go back in. What did you have to do on the sender side in terms of maintaining state? What additional stuff? Because nothing is free, right? No free lunch. Okay? Alternating bit is cool. Go back in is cooler, but you got to pay a price. In terms of sender, what did you have to allocate? The sender had to allocate a window, right? Yeah? So you need buffers, yeah? So you need to allocate, you need buffering. Of course, in your case, it was simple. You know, the window size was so small, but typically, yeah, in a byte stream, it might be fairly large, right? So you need buffering, okay? And buffering, and you need to keep track of unacked packets. So this is the sender and ACK packets for receiver in selective repeat, right? So you had to add buffering both at the sender and the receiver, and you had to keep track of which ones were ACKed and unacked, right? Okay, so that made things more complicated. And the other thing that you realize is that we need to understand the relationship, right? Versus sequence numbers. And if you get this wrong, which a fair few of you did, would have got things wrong in your prac, right? If you didn't have this relationship understood very well, okay? I am going very slow in these lectures, but it's okay. We have week 13. I may have to ask you to come back. A small warning. Okay, so why did we guys prime you up with go back in, alternating bit, selective repeat, all this stuff was really leading up to talk about TCP, right? Because those are, you know, just simple protocols that allow you to understand how reliable transport works, leading up to how TCP implements reliable transport. So the TCP packet header, just to recap, here's the UDP packet header. It's extremely simple, right? Source port, destination port, length, and checksum. But, right, crazy. So why does it need all that stuff? Simple, because it has to do connection establishment, connection termination, and it has to do reliable transport, right? That's why it's complex, okay? So nothing is free. So you pay a large overhead in terms of your packet header compared to TCP and UDP, right? Just because you need to provide all these services, right? Okay? So the protocol needs to support the services. Reliable transport, connection-oriented, blah, 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 okay? So that means all of these headers have some kind of function, and we'll see how that comes together. Source port, destination port, looks good. So sequence numbers, you know why that's there for, right? Acknowledgement number, so that is receiver acknowledging the receipt of a sequence number, right? So there's a bunch of new stuff called receiver window size, which we'll look at. And checksum, you already know about. This was common across UDP and TCP. It's a way of detecting when packets are corrupted, okay? Then TCP has a variable length header. So what that means is that for future-proofing the protocol, there are options that you can also include. Then there's a whole bunch of, so because it's variable length, there is a field called header length, right? So because it's a fixed size header. So any protocol, typically you'll find that if it has a variable size header, then it would need to indicate to the thing that's going to process that packet how much header information is there, right? There's a price to pay, right? If you had a fixed size header, processing is faster. You know exactly how how many bytes to read and process. But if you don't, then that means when you get a packet, you got to go find this guy, figure out what the length is, and then load that header, and then figure out what options are there, etc., and process that, right? So you pay a price for having a variable length header, right? Pay a price for flexibility, okay? Just a side note. So there's a whole bunch of flags here, which you'll understand in a minute. So U is for urgent. This is not typically used, and because when we design stuff, you don't want to design stuff thinking about what we need now, but you also think about the future, because if you had to redesign the protocol or change the way TCP works and have to re-upload and update kernels of all the machines on the internet, might not happen, right? So you need to future-proof your protocol, right? And think about what might be needed and have some flexibility to support that. So some of the stuff are not used but could be used. Then there's a push-through, again, generally not used. But what is used is this stuff here, RSF, which is to deal with connection establishment and connection teardown, right, which we will look at, okay? And we will look at this guy here. There should be one more, which is, yeah, that one there. This is, nope, not going to look at in too much detail. So what are we going to, in terms of TCP, the stuff we're going to look at are, one is, of course, reliable transport. So you know all the mechanisms of reliable transport now. Look, TCP uses all of them. Actually, TCP uses a hybrid between go backend and selective repeat. So what's cool about go backend compared to alternating bit, pipelining, and one timer, and what's special about the acknowledgements? Cumulative, right? So that's kind of neat, right? If all the acts before it fails don't care, if the last act arrives and it acknowledges everything else, right? So you can shift your entire window technically, right? So that's kind of cool. But what's the problem with go backend? Huh? Sorry? Uses a big buffer, but well, selective repeat does too. But what's the problem with cumulative equivalent? Yeah. Yeah, failure is expensive, right? So because you can technically end up retransmitting the entire window, right? When you don't need to, right? So selective repeat solves that by acknowledging individual packets, right? So TCP does that, but combines that with cumulative acknowledgement, right? So it does acknowledge individual sequence numbers, and the sequence numbers it acknowledges is cumulative. So it combines best of go backend and selective repeat. And that's the reason we looked at those two protocols before we looked at TCP. Okay? So essentially it's a mix of GBN plus selective repeat. And but the difference is that the way acts work is a little different, right? So we'll look at why that is. The thing that's new to you guys, which we haven't looked at, is flow control, okay? And this is important because you have a sender and a receiver that is maybe sending stuff back and forth, but if the sender sends too much stuff, the receiver gets overwhelmed. You've allocated buffers. You've seen how hard that is to maintain a buffer. You've seen what happens when the buffer gets full, when you did go back in. Stuff gets dropped, right? So you don't want your sender to be sending a whole bunch of stuff when you can't receive them because you haven't allocated enough memory space or there is not enough memory space, right? So how does a sender and receiver communicate how fast to send, right, stuff? Okay, that's about flow control. The other one we're going to look at is congestion avoidance. Hey, so you know, sometimes the network is really slow. There's a lot of stuff going through. And then what would happen, you know, it's like leaving university at 5:30, right? It takes me about, you know, to go home might take me an hour and 15 minutes if I leave at 5:30 because everyone's on the road at the same time. But if I leave at around 6:37, I go home in about, you know, 30 minutes, right? So if you understand congestion, right, that means there's no point trying to send a lot of data when the network is congested, right? So it's nice if you can somehow deal with that, right? okay? Because you make matters worse, right? Everybody leaving at the same time just makes matters worse. All the roads get congested, right? The other thing we're going to look at is something you've already seen, which is connection establishment and teardown, right? So this stuff is a little new. Reliable transport, we spend a lot of time looking at, so you guys should be all experts. So connection establishment teardown is important because we've mentioned from the beginning that TCP is a connection-oriented protocol. UDP didn't do that, right? And there's a whole bunch of stuff around how to make sure that the connection is established and both parties agree, etc. Okay? So the first thing we'll look at is, look at why the reliable transport stuff, why that's different. Sequence numbers. So here's the kind of get your head around this. Why I said sequence numbers is a little different is because, so here's a simple example of a byte stream created between host A and host B. They're sending 1 byte of data. So in TCP, sequence numbers are essentially numbers of bytes, right, that you're sending back and forth between each other, right? So you label the bytes, right? So in the starting point, what you're sending, a byte stream number is the first byte in the segment's data. So that means you got something to send on this side, right? So that byte is, say, byte 42. So you send the sequence number as 42, right? And your acknowledgement, so you can also piggyback an acknowledgement. The reason why you can do that is if you look at the TCP header, there's a flag called A. So that is if it's an acknowledgement. So if you set the A flag, that means you're piggybacking an acknowledgement, right, in this packet while also sending a sequence number, right? So you can send both of these pieces of data at the same time, right? Okay. I can acknowledge what I received and also provide the sequence number for the data payload that I'm sending. Okay. I can do both at the same time, right? This flag A says that there's an acknowledgement that's being piggybacked, right? So essentially, my starting point is that I'm sending a byte stream where I am at byte number, if you like, 42, and I'm acknowledging, acknowledgement is a little funny, I'm acknowledging 79. That means the acknowledgements actually tell the sender the next byte expected from the other side. So that means I have received byte stream number 78. And I'm acknowledging 79 because 79 is what I am expecting to receive. Okay, so it gets a tiny bit trickier. So what should happen here is that this host here echoes back what it receives. So essentially when it sends a packet back, you'll see that the sequence number is now 79 because what I've said here is I'm expecting byte stream byte number 79. So that's a sequence number I'm sending. And I'm acknowledging 43 because I've just received 42, what I'm expecting next. So this is the next expected byte is 43. So remember, I'm always acknowledging the thing that I'm intending to receive, right? So because I told you TCP does cumulative acknowledgements, what that means is that if I get 43, all the other bytes before that has been correctly received, right? Okay. So when the sender sends back, essentially now my sequence number, so I'm acknowledging 80 because I've received 79, right? So next one I'm expecting to receive is 80, okay? And the sequence number that I'm sending is 43, which is the one that's the host B is expecting, right? Was this confusing? Because it can be a little confusing, right? So you always acknowledge the thing that you're expecting. That's it, right? That's the tricky part, okay? All the ACKs are for the byte stream that you're expecting, okay? The next byte, right? The other thing about TCP is TCP does handle out-of-order segments, but the specification doesn't really say how that should be implemented. But that you should realize by now because you've seen a number of specifications which describes the behavior, but actual implementation details are left to you, right? Okay. So that means you can get these packets out of order, and TCP will reorganize them in the right order, right? Okay. Is this clear to you? So the key difference is you always acknowledge the byte stream that you're expecting next. Okay? Yeah. So that's a little different to what you've been doing so far. Okay? So small example. Let's look at the retransmission scenario in TCP, right? Remember, reliable transport uses timeouts, which you guys are familiar with, so does TCP. So this is a little bit more complex, maybe. So your sequence number is 92. That's the starting byte, right? So this is the starting byte for this packet is 92, right, in this byte stream, and you're sending 8 bytes of data. So it's 92, 93, 94, 95, right, up to 100, right? Sorry, it should be 90, 99, right? So, and then the sender acknowledges the, remember, the acknowledgements are the sequence number of the next byte expected from the other side is in your acknowledgement, right? Okay, so the sequence number of the next byte expected is 100, right? Okay, and if this ACK is lost, so we have a timeout, and then after the timeout event, as you expected before, you have a retransmission of the same byte, and eventually the ACK arrives, right? So I think we briefly talked about it when we introduced timeouts, and we had a small discussion about how do we get this number right? Right? It's tricky, yeah. So if it's too small, it's a problem. You have this problem, which is premature timeouts, right? So in this case, you can see that you send a packet and start timing, right? Here's the ACK, but before the ACK arrives, you have a timeout event, right? Okay, so you retransmit. Right, and then eventually the ACK arrives, right? And then you have the second one that was sent, which is acknowledged, cumulative acknowledgements. So you have 120, but you can see that this was unnecessary, right? So I guess the simple point is that if you have timeouts that are too short, even in your implementation, you'll see a large number of retransmissions that are unnecessary, right? What would happen alternatively if the timeout is too large? I mean, we could have increased this timeout to be, maybe somewhere here, right? Here's your timer. So why not do that? Why not just make the timeout just large? What's the problem with that? Yeah, so for the cases that stuff gets lost, you have to wait a long time to figure out that stuff got lost, right? So, there's no silver bullet, right? There's no perfect number that you can come up with and say, oh, this is going to work. Because why is so hard to get a good timeout value? Why would it be so hard to get a good timeout value?
Because we don't know what delays the packet's going to get.
Yeah, it's, we don't know the number of users, we don't know the nature of the traffic, it's dynamic, everything is changing. So you can't, right? You can't pick a number, and whatever number you pick is going to be wrong at some point. Maybe right for now, but it's going to be wrong soon, right? Soon it might be too short, soon it might end up being too long, right? So it really depends on the nature of the network and as a sender and receiver, right? So you're sitting here and here, but in between you is this kind of giant network, right? Which you have no idea about. Who knows what's going on, right? All you're seeing is just stuff popping out your network link, but somehow you got to determine what this value ought to be, because TCP runs on the end systems, right? Okay, it makes the links between two end processes, remember, right? And those two processes have to somehow understand what's going on in the middle, right? Okay, it's difficult to do, right? I mean, all you see is packets coming in and out. So setting this timeout value is hard, and you'll see how TCP does it, right? So how long should a timeout be? This is an interesting question. Okay. Timer should time out only rarely, obviously, and ideally only when a segment is lost. So perfect world. Timeout only happens when a segment is lost, but that's never going to happen. The way that we talked about how to set a timeout last time was, you guys came up with, was we could use the round trip times, right? Because we know how long it takes between the time you send a packet to getting an acknowledgement, right? So that gives you an indirect measure of what's happening in the network in the middle, right? If the acknowledgement is taking a long time, it would tell you that the network is busy, it's slow, right? There's no point setting a short timeout period and timing out and creating more traffic by creating more retransmissions, right? Okay? So the way, and the reason that this is difficult is because TCP runs on end systems and has no idea about what's going on in the middle, and it has to somehow sense what might be an appropriate value to use for timeout, which is the sender and the receiver, right? So the way it does that is by using estimating the round trip time, which is something that the end systems can do, right? It can measure and time how long it takes to get an ACK. Of course, it gets a little complicated because, TCP, it's a byte stream, there's cumulative acknowledgements, all that kind of stuff, right? And then determine what might be an appropriate timeout to use based on what you think is a good value for the time it takes for a packet to go from A to B and B to and go to A to B and B to A, so which is a transmission and acknowledgement. So the way it does that is by using it measures a sample RTT, which is essentially the time between sending and receiving an acknowledgement for the current packet, and it uses a kind of a moving average, right, value. This is a historical value, right? Okay, so it's a weighted moving average essentially between the current estimate and a previous estimate, right? And you can see the weighting factor here. So this is the weight. It gives it to the current estimate, estimated RTT, versus so this is the new estimate from a recent transmission and acknowledgement, right? So this is nice, and you'll get to do this in Wireshark, and you'll get to try and estimate, actually calculate this value based on looking at a packet trace, right? So I have about 10 minutes. So this will return a hard number, right? Which is, you just get a single value, okay? What's the problem with that? I just got one number, I don't know, 5 milliseconds is my estimated RTT after doing this weighted moving average calculation. Why don't we just use it? Sorry?
The nature of the network.
Yes, exactly. So because the nature of the network, that one time might be 5, and one time might be 10, it might be 5, it might be 6. So essentially, it can still cause too many frequent timeouts by picking a single value. So TCP tries to be conservative, and it actually calculates what might be the expected deviation from the estimated RTT, right? So this is the so instead of just using the single value that you just calculated, right, based on your based on your most recent transmission and acknowledgement, it says, well, networks don't behave so well. Maybe my estimate is 1, but it could be within a range, right? How do you know it's always going to be 5? I just estimate it as 5. It's a perfect number. So what it does is it creates some, it tries to assess the variation, right, of this estimated RTT, right? So the way it does that is to also create the deviation from the moving average, right? as a weighted, again, weighted average between the current, so this is the deviation. So this is deviation based on the current measure, and this is your, of course, this is your historical value, if you like. Right. So it tries to determine how best to evolve this deviation, right, from the estimated RTT. And you can see it's a very kind of very conservative in terms of, because you take 4 times the deviation, right, as your timeout interval, not 1 time or 2 or 3. So it's like, you know, it's like saying 4 times the standard deviation, right, is what you're happy with. So you need, the reason why you do all this business is because the dynamic nature of the network, and you cannot pick a single value which may be right in this instance but wrong in the next instance. So the point is, how do you dynamically estimate an expected RTT that will work well under different networking conditions? And you don't want this value to fluctuate too much, because that means you have we'll get strange behavior from your network, right? So you do want these values to evolve, but you don't want them to evolve rapidly, right? Okay. So what's a good way of doing that is to estimate what you think is a round trip time, and then create some leeway between what the variance of that value is, right? So this is the variance of that value, okay? And in your next Wireshark labs, you'll be able to do this calculation by hand by using a packet trace, right? Do you have any questions about this stuff? This is, of course, one way of doing it. You know, I'm sure you might have better ideas doing this. So, I mean, I'll discuss this some more when I come back on Friday to the lecture with a question. But for now, just let you guys digest that, right? Okay. The other thing that we talked about that we want to do is TCP does is flow control. Okay. So why is flow control important? Because you don't want the sender to overwhelm the receiver, right? So how does it do that? It does that by the sending process. So you guys already used a buffer for the sender and go back in, right? And the receiver had a buffer of 1, so it's not a good example, but if you did selective repeat, then it would have been a better example. But so in go back in, you have a buffer size of 1, but if you had selective repeat, then you'll see that the receiver actually has a buffer size of W, which is the same as the sender. And if the sender was to send too many packets, then the receiver window would get full, could get full. Why would the receiver window, how could the receiver window get full? Why would it get full? Sorry? Repeated acts. No, acknowledgement doesn't cause that problem. So you get a lot of packets, and why would my receive window in selective repeat, for example, become full?
Because it's still waiting, or it's still sending acts through.
What happens to the packets in your in assignment 2 that you got to the transport layer? What did you do with them? What did the transport layer do?
Send them to the application layer.
Send it to the application layer. So how did your buffer empty? Your buffer emptied when the application layer picked up a packet, right? Who controls that? Does the transport layer control that, or the application layer control that? Who consumes the data? Application layer. So does the transport layer control that? You did the web server, right? Right? You guys wrote a web server, and who consumed the data? The client or the web server, right? So the transport layer has no say in it, right? Just put stuff there, and the application layer consumes that data. So if you imagine this is your buffer, right? Receiver buffer, and this is filled. This much is filled, so which is this difference here, right? So this difference here is, so this is the spare capacity, right? So this is your spare capacity, and this much is filled. And so if this is the front, I don't know, am I doing this right? This is the back, 5-4 buffer. So the application layer, application process is the one that removes this data, right? So you have no control over that. And if the application process is running slow or not consuming the data, this will just keep growing, right? Okay, this will just keep growing, and eventually it'll be full, and then you're stuffed, right? But if you look at the sender and the receiver, the sending process has no way of seeing what the receiver buffer is, right? Okay, I can't see the receiver, right? Blind. Okay? The sender doesn't know how much stuff, what this application is doing on the other side, how much is filled here. So how do we communicate that information, right? Well, TCP has support for that, right? If you look at the protocol structure very carefully, you'll see what's called the receive window size, right? Okay? So TCP allows a mechanism for the receiver to communicate how much buffer space is left to the sender by using this header field, right? Okay, so what it essentially does is it fills the available receive window size into this space here, okay, when it sends an acknowledgement, for example, right? So that means the sending process can it can sense, right, the available buffer space at the receiver. Okay, how does it do that? It looks at the receive window size, right? Okay, so that means the sender can throttle, if you like, right? Throttle, like accelerator, motorbikes, anyone? So it can reduce or increase the sending speed, right? Okay, based on how much buffer space is there, so I don't overwhelm the receiver. Yeah. So simple concept, right? Can you see how beautifully that is translated into the protocol, and that the simple idea allows the sender and the receiver to achieve flow control, right? Okay. So here's my question to you before we finish in 2 minutes: is what if this application is so crap, bad, died, whatever, and this thing is grown all the way up to here, and I'm completely full, so when I'm sending TCP packet back, I set I do have another color pen, don't I? Oh, sorry, I really want to do that. There you go. I wanted to use it. So, what if we set this to, this is the receive window. What if we set this to 0 and send a packet back? So the receiver goes, ah. What happens?
Would it wait for the timeout period and then given a timeout error?
Who will wait for the timeout period?
The sender.
So technically, sender knows I can't send anymore because this guy's window is full, right? So what could we do? Because the only way we sense how much space is available is by using this acknowledgement, right? But now we're not going to get any acknowledgement back, right? We could, but we can't send anything. So technically, the sender is supposed to completely throttle the link, right? That means not send any back. So what you're saying is have some timeout and then try again.
Oh yeah, maybe after the timeout, if there have been no acknowledged packets received, you just begin the connection instead.
Okay, so right. So one idea is, so if you ever get a receive window size of 0, which tells the sender I can't send anymore, but I'm just going to back off and wait for a while, and then when I time out, I'm gonna send a packet back. Right? What shall I send back? Which packet shall I back? What shall I send back? Is that the